I was like, I'll do that one. But then I just guessed.
All right, guys.
I guess like,
That'll work.
but I definitely like, I guess I was better.
All right, we're in a different place than my seventh period.
Are we ahead? No.
We're actually a little behind. But not much, like 5 minutes maybe. But I did a couple extra problems with them, but I don't remember. Have we talked about the difference between a permutation and a combination?
Yes.
So we know that permutations are talking about counting the number of ways something can happen if what?
The order matters.
So if the order matters. And again, be careful. What I do not mean when I say order matters, like obviously if I'm dealing cards, say to Spencer and Ella and Anderson, if I'm dealing cards out, the order in which I deal them matters, right? They're going to get different hands if I deal. That's not what I'm talking about. When you decide between permutation and combination, we're talking about, say, the cards that Spencer receives. Did the order in which he received them matter? Did it affect the outcome? And it depends. There are some card games where it does. And I think we talked about war. If you're playing war, it certainly could matter the order that he receives them, because as he's playing them, or the order that he's playing, because he's not really looking, as he's playing them, the order in which they show up could affect the outcome. So most of the time with card games, and in all the card games you guys will have on your test, we're talking about like poke hands, things like that. If you're not familiar with that, we'll go over all of that. It's not overly difficult. It's pretty clear. But those would be examples of combinations. Okay, so the order in which you receive those cards wouldn't have an effect on the actual quality of your hand. But the main difference I want to point out with combinations and permutations is a permutation, right here, a permutation like NPR is n factorial over n minus r factorial, but a combination NPR is n factorial over n minus r factorial. Looks exactly the same, and then an extra r factorial. But there is no, at all, there's no combination permutation that has n factorial over r factorial alone. That's it. And if you really think about it, when you look at this NCR, it's really what? It's the permutation, n factorial n minus r factorial. It's really the permutation just divided by an extra r factorial. Are y'all seeing that? Now, it's not super important that you see that, but you're going to see soon, and I think I've mentioned dependent and independent. And we talked about independent situations were situations like flipping a coin, right? Because getting ahead on that first flip has no effect on the next flip, does it? Or rolling a die, say getting a 4 when I roll the die has no effect. Now, if I rolled a 4 100 times, I might think maybe I have a loaded die, right? Maybe it's weighted on one side that's causing the 4 to show up more. That might be true, but we're not getting into situations like, well, actually, there might be a bonus. There may or may not be a bonus with that kind of play. But anyway, what happens in a dependent situation allows me to use these. Because in a dependent situation, like, hey, when I draw a card, the card that I draw is going to affect the number of ways that other things can happen because there's one less ace maybe, or there's one less 10, right? And it affects the probability as well when we get to that. So in dependent situations where what happens on the first draw affects the second draw, et cetera, et cetera, et cetera, those are situations where I can do this. I can use permutations and combinations because you can see the numbers are decreasing, right? 52 cards, 51 cards, 50, 49. It just reeks of a factorial. Are y'all seeing that? But if I am putting the card back in the deck so that there's still 52, 52, 52 each and every time I draw, or there's still 4 kings, 4 kings, 4 kings, even if I'm drawing a king and putting it back, you cannot use permutations, combinations, or anything in those kinds of situations because the numbers aren't decreasing. And if they're not decreasing, you don't have factorials, and these are nothing but factorials. Are you with me on something like that? So anyway, make sure that make sure, as we go through these, really focus on addressing 2 things. First, you look at the problem and you go, is this a dependent or an independent situation? If it's dependent, I've got a shot at using these, and that can really help me I mean, you'll see it as we get to these problems. It can really shorten my thinking. All right, but if it's an independent situation, take a step back and go, all right, these are off the table. I've got to address each and every outcome separately. And you'll see that. And sometimes there's ways to simplify that too. And then if it is dependent, well, then I can walk over here and now decide, all right, does the order have an effect on the outcome? Does it not have an effect on the outcome? And I could further decide which of these I can use. And again, we're going to do so many of these. If you're doing the homework and filling in the blanks, redoing the problems that I'm skipping and asking questions, I think you'll be in good shape. Or hopefully you'll be in good shape. Anybody got any questions on where we are up to this point? Okay, so I think what we were doing is talking about which of these were combinations of permutations. Which one? What did we even get to? We got through 25? We did?
No.
Oh, well, then we're not too far behind. Okay, so as long as you understand stuff like this and you can actually decide, because if you see a problem and it's got one of these situations in here, you've got to be able to look at it and go, is it a combination or a permutation? And again, I'm going to avoid things like sitting students in a row where, yeah, the order might have an effect on the outcome. If I have, like in basketball, like if you got guys on the bench, you usually got the guys that you want to get in the game nearer to you. And you got the guys that aren't on scholarship that are just the dudes just barely made the team or whatever. They're at the end of the bench. I'm probably not going to be playing them too much. So having them in that order, the order in which you arrange them could have an effect on the outcome. Discipline issues in kindergarten. If you got a couple guys that are cutting up or whatever, maybe you want to separate those. So sometimes they could have an effect, sometimes they are not. And again, I'll try to avoid those or really clarify with words like how many different unique arrangements. So if I say things like unique arrangement, that suggests what? Permutation. Because if it's a unique arrangement, that would suggest that the order in which I arranged them would have an effect, right? If it's unique. So if I say the word permutation, obviously it's a permutation. But if I say unique arrangements or even arrangements, it's suggesting that the order would have an effect on the outcome. Those should lead you to permutation. And again, most people don't have a lot of trouble with this. When I say most, I mean very few people have trouble with this by the time we get to the end because you've done so many of these, you become familiar with them. All right. All right, circularity. So circularity, I would love to do a better example than this. And I tried once, and there were just so many options. There ended up being 24 of these little circles. And people were like, whoa, their brain was like an overload and it didn't make sense to them. So here's what I want to talk about, circularity. Okay, so when you arrange people in a line, and you can visualize this pretty easily. Let's just say I had A, B, and C, person A, person B, person C, and I'm arranging them in a certain order. Well, clearly I could have ABC, I could have ACB, I could have BAC, I could have BCA, I could have CAB, and I could have CBA, right? And that's 6 different ways, or 3 people choose all 3, which is the same thing as 3 factorial over 0 factorial, which is just 1. That gives me 6 different ways to arrange those people, right? And you can see that those are all different. Well, if all of a sudden I go, all right, I'm not putting them in a line, but I'm putting them in a circle. And when I say circle, I don't mean it actually literally has to be a circle because it's 3 people, right? Really makes more of a triangle. But what I mean is when I arrange them in such a way that's kind of circular-like, whether it's circular or triangular or pentagonal or whatever, when I arrange them in a way like this, where basically think of the 3 people sitting at a round table, spaced apart or whatever, and they're all looking at each other, but they're completely ignoring their surroundings, okay? So if they're completely ignoring their surroundings, or think of like a necklace that has no clasp, and you have I'm trying to think of a decent example. You guys don't know what atta beads are, but like back in the 80s, girls would wear these gold necklaces. Do y'all know what I'm talking about? Somebody does? Okay, they wear these gold necklaces with these little beads, and they were just hollow gold beads, and you would add a bead every now and then, and the more beads you had, the cooler you were. I mean, it's totally lame. And then these little, my wife had them, I remember. I mean, I didn't remember my wife. I didn't know back then, but she had them, and they would get dented. You know, like you'd bump into something, you'd have a dent in your big gold bead and you'd cry because they were expensive or whatever. But you would add these beads and you were like really cool for the beads you had. Well, the beads were just round, hollow beads. And the idea on these beads was you just get a bunch of them. But the point is, like, let's just say I had 2 small beads, 2 big beads, and another 2 small beads. And I'll say, well, how many different arrangements? Well, if it was linear, right, if you had linear arrangements, then this would be different than that, wouldn't it? It's a different arrangement. But in a circle, it's really not, because I can take this one, swing it around to this side, right? And I didn't really arrange them on the necklace any differently. They were just on there. It was just the way they happened to look. Are you with me? So when I put them on my necklace, I didn't have to put it in a different order like I have right here. All I had to do was just swing a small one over there and I had this bottom situation. So a lot of the things on a necklace, on a round situation, would be the same, even though they might look a little different because I could just swing a bead around. Are you kind of following me what I'm saying? Think about it with people. Let's just say I had the 3 of you at a circular table, right? And Spencer's like, all right, I got Ella to my left, I got Anderson to my right, right? So right here, think of, I'll tell you what, let me use, we'll call this Spencer, and we got Ella, and we got Anderson, okay? So right here, he's saying, I got Ella to my left, I got Anderson to my right. Are you with me on this? Okay, this is an example of like ESA, if you think about it, right? But couldn't you also think about it as AES? You got ESA, AES, SAE. You've got all kinds of situations which are really the same situation. Linearly, they would all look differently. But from a perspective of this, it just kind of depends on the perspective of the circle. Are you kind of following me on this? Well, I want to show you that these are 6 different ways to arrange ABC, but they're really not 6 different ways. Because if you think about it like this, all right, from the perspective of person A has C to the left, B to the right, right? Well, what is this? C to the left, B to the right. So this right here is the same as that. And what about this? C to the left, B to the right. That's the same thing as this. Are you with me? Or what about this one? I have B to the left, C to the right. But look at this. B to the left, C to the right. Right here, B to the left, C to the right. So the reality of it is I really don't have 3 factorial situations when they're circular. I just have 2 factorial. Well, this is not a proof, but whenever you have a circular situation with no clasp, and no clasp on a table, I guess would mean something like, I don't know, there's no object on the table obstructing view. Maybe there's no seat in which A has to be stuck. And I'll give you examples like this where A isn't moving, but everybody else is moving. Some situations on a table, and I'll give you some examples, take away the circular nature of the table, okay? But if anybody can sit at any seat and you can just move around, the way you calculate the number of ways is you're not going to say 3 factorial. You're not going to do that when it's circular like you do when it's linear. You're going to say 3 minus 1, then factorial. And you can see in this situation, that gives me 2 factorial, which is 2. And there's really just these 2 unique situations. Because if I want to go from this A, B, C to this, what did it come from? To this one, B to the right, yeah. To this one, B, C, A, all I got to do right here is take these and just turn them. I just rotate them around. It's really the same thing. What that really means is you can take 3 car keys, assuming that you could open stuff both ways. You know, you could flip it over if they were like flippable. If you take 3 car keys and put them on a keyring, it's the exact, well, there's not 6 different ways you can arrange them, there's just 2. And we're going to talk about flippable in a second. You're going to see it's really just 1. So I can basically get any possible situation with 3 car keys once I am able to flip it as well. It's the exact same thing. I put them on, then you're like, oh, I didn't want that one first. Okay, now it's first. Well, I didn't want that one in the middle. Now it's not in the middle. You can flip and turn and spin, and it ends up being the 3 ends up being the same as 1, but you'll see that. Now, 4 doesn't end up being the same as 1, but I'll talk about those. So bottom line, if you find that you have a circular situation, people sitting at a table, okay, there's a couple other ones I'll throw at you. If you have that, instead of saying, oh, I'm arranging 3 letters, 3 factorial, you go, no, 3 minus 1, then the factorial. If there's 5 letters, instead of 5 factorial, 5 minus 1 is 4 factorial. Are y'all seeing that? Now here's how it gets broken up. If, for instance, there's something about the problem that suggests that, like in real life, we know this is probably not true. Like if I have a big round table and like, for instance, when I go to eat with my wife, she always wants to have the best view. Like I don't care. You know, I mean, I care maybe this much. She wants to sit where she can see everything. You know, like we went to Pizzeria GM the other night and they put us in that back room. I don't know if y'all been there. You walk through and it's like a back little kiddie room. And she was breaking down. Like, I mean, she has to see beauty or it's just no fun for her. Now I know my wife well enough. I'm like, hey dude, you got a better table than this. He's like, oh yeah, sure. So he brought us out somewhere else and she had peace. Okay. So for her, a table, the perspective means something. But what we're saying is if you take away the perspective, okay, you take away the surroundings and all you're focused on is the people at the table, those arrangements, then if it's circular, then you apply this rule. But if there's something like, wait, there's light shining in at one corner. Well, if you start introducing extra stuff there, then yeah, now the perspective includes the light, right? Like I don't like sitting outside in the sun if the light's in my face, I'm miserable. My wife just loves it. She's dark complected. She loves just absorbing the rays. I'm made for the high country, right? I don't want to burn. I burn in 20 minutes eating lunch, whatever. So I'd rather have the sun in my back. So those kind of things, I'm talking about, you take all those out of the situation, and if it's circular, you apply this rule. Are y'all with me on this? Okay, so like if I said, for instance, let's just say you had 10 people at a table, all right? So if I have 10 people at a table, just arranged, and I said, how many people, how many different unique arrangements can I make? I'm not going to say 10 factorial or 10p10. I'm going to say 10 minus 1, 9 factorial. But what if I said, hey, I got 10 people, but Biff has to sit in this seat. If Biff has to sit in that seat, and then I'm saying, okay, how many ways can I arrange the other 9? So if I say that, Biff being locked in is almost like breaking the chain. And if I break the chain of this right here, I'm basically dealing with a linear situation for the remaining 9. Now, Biff is locked in, right? We got Biff right here. It's almost like there being a clasp. We'll talk about clasps on circles or whatever. If there's something on it that keeps that just from, like, almost like if I'm trying to rotate, like right here, I could take A, swing it up here, B, swing it over there, C, swing it over here, and now I have CBA. Well, that's what I have right here, just by swinging. But if there was a clasp right there, I can't swing B over there, can I? Well, I mean, if you're like, well, you gotta just put the clasp, but if you wear a necklace, nobody wants the clasp right here, right? Unless you have a really pretty clasp, I suppose. But typically, you don't want the clasp in the front, you always want it in the back. So with that in mind, if there's something like Biff having to sit in this seat, it keeps me from able to swing people around and change the order that way. You tracking with me? So I would say, all right, Biff's locked in, but there's 9 people left, but the 9 people are no longer in a circular situation. Regardless of the fact that they actually look circular, I would just say the remaining 9 is just 9 factorial. Which I know you're thinking right now, wait a minute, but that's the same thing as doing 9 factorial up here. In this particular situation, yes, it was. But what if I were to say something like, all right, I still have 10 factorial, but there's this open seat that nobody can sit in, right? Keep that seat open. So how many ways do you arrange these other 10 people? Well, it's circular, but that open seat change the perspective of being able to, because right now, like if this person right here has open seat person, if I jump to there, now I have person open seat. That's different perspective for that person. So I would say, hey, the remaining 10 people, the 10 people are still 10 by 12. All right? Now, what if the situation is circular perhaps, but I could flip it as well, like a necklace? All right, now, I know a lot of things that you put on a necklace may be pretty on one side and not pretty on the other. All right, if you're wearing some jewel or something, or I don't know, whatever it is, a lot of times if you were to take your necklace off and flip it and put it back on, you're looking at the back, right? Maybe the ruby or emerald is on one side and there's just crap on the other, like whatever holds the clasp, or I don't know, I'm making stuff up. But when we say if you have a necklaces ideally we say they're flippable. Keys, a key ring is flippable, right? I can't flip a table of people, at least not comfortably, right? That's not a really flippable situation. Well, if it's flippable, that's like me doing this. Remember we boiled it down to these two? What if I pick this up and flip it over? Like literally, I pick it up and flip it. I would have B on this side, right? A and C would kind of still stay in the same place. Now think about B's perspective. Isn't that A to the left, C to the right? A to the left, C to the right. So if I flip it, I basically just cut this in half. So if it's circular, we're going to go n minus 1 factorial. If it's flippable, we're going to divide by 2. And it may be both. It may be one without the other. Like if I have a necklace with a clasp, is it considered circular? No. So if I had 10 charms or atta beads or whatever on my necklace, 10 factorial. But because it's flippable, what do I do? Divide by 2. There might be things that are circular, like a table. 10 people at a round table, nothing else going on. 10 factorial. It's not flippable. Don't divide by 2. But I also might have a necklace with no, or a keychain. What if I had just a key ring, just the ring, and I had a bunch of keys on it? Right? If I have a bunch of keys on it, that is circular because I can move the keys around to change order without really changing order. They're on the same situation, I put them on the same way, but I could also flip it over and get a different order. That's both. I would subtract 1 and divide by 2. Y'all seeing that? I think this is pretty straightforward. Most people do pretty well with this. Make sure you're good. Don't just kind of go, oh, I don't know, I think I got it. I keep missing them, but I think I got it. If you're missing these when you're doing them, talk to me and let's straighten you out. And I'll just give you enough examples that you get it straight in your head. Although I think I did do that if you're doing most of these. All right? So anyway, like right here, how many seating arrangements can be made for 10 people sitting at a circular table with 10 chairs? Well, it's circular, right? Is there anything about that problem that suggests some clasp-like situation? No, so it sounds very circular. Not 10 factorial, 10 minus 1, which is 9 factorial. Now, can I flip a table? I cannot, so don't divide by 2. You're done. How about this? How many ways can 8 charms be arranged on a necklace that has a clasp? Well, if it has a clasp on it, that keeps me from being able to rotate stuff around. So technically, is it circular? No, and think with a clasp, you could unclasp it and it's linear. So it's really a linear situation. So what? Just 8 factorial. But because it's flippable, necklaces, key rings, that kind of stuff, what do? Divide by 2. But if I get rid of this word, has a clasp, this phrase, if I just say how many ways can 8 charms be arranged on a necklace, and that's all I have, what would you do then? Yeah, 7 factorial over 2. So it's really not overly complicated, I don't think. I will throw a curveball here or there, but I'll throw those curveballs ahead of time on homework problems to give you a look at them. So hopefully on game time, you will not be intimidated. All right, so how about number 28? How many unique ways can Johnny, Biff, Rhonda, Julio, and Fred be seated at a table? You what? I can't hear you, I'm sorry.
Oh, how many people are there? 5?
1, 2, 3, 4, 5.
34.
So 5 minus 1 factorial, 4 factorial. I'm not dividing, right? Not dividing by 2 because it's not flippable. If Johnny has to seat nearest the door, all right, now I got a situation where Johnny, say this is the room and there's the door right there, right? So Johnny has to sit right here. Well, what am I really arranging now? The remaining 4, right? And the remaining 4 are sitting in a situation where Johnny is kind of acting like what? He's acting like the class. Okay? So if he's acting like the class, then I'm basically saying this is a linear situation for the remaining 4. Johnny's not being arranged, right? So what do I end up with? 4 factorial. Now, I know you look at that and you're like, that's the same thing. That's really annoying. It is. If it helps to make it unannoying, what if I said, hey, the table nearest the door, right? The seat nearest the door has to remain open. How many ways can the remaining 5 be arranged? Then it's not linear 5 factorial. Are you with me? So you just have to look at the problem and kind of see what's going on. And I think you'll be okay. How about this? Barbie has a claspless bracelet, and she wants to, I don't know why I didn't connect that. And she wants to attach her 5 different charms to the bracelet. How many unique ways can the charms be arranged? Is it circular?
Yeah.
Claspless, right? So if it's claspless, I know it's circular, so instead of 5 factorial, I go 4 factorial. Is it flippable? So divide by 2. And again, we're not simplifying any of this stuff. Now, let's look at number 30. Read number 30 and tell me what decisions are you having to make here. There are really 2 decisions, but you can do it in 1 fell swoop, or you can do it in 2 fell swoops. There are there's 2 30s. Sorry. Second 30. There are 10 students in a class that meets in a room that has 12 chairs. All right? How many ways is it possible for the 10 students to be seated? Now, what decisions are you making? What are you having to do? Like, say you're the teacher and you're arranging these people. What 2 things are you deciding? What? Okay, the order that you're seating them, and then what else? Which chairs? That's 2 picks, right? Okay, now let me ask you a question. Let's just say there were 10 of you. And I come in here and I'm like, all right, what seats do I want you to sit in? How about that. Oh, wait. How about that. Isn't that the same thing? So when I choose the chairs, does it really matter what order I pick those chairs? So if there's 12 chairs to pick from, and I want to pick 10, how would I say that? 12C10? And we know that 12C10 is the same thing as 12 factorial over what?
12 minus 10.
12 minus 10, which is 2 factorial over, and still over 10 factorial. Okay, so I just picked the chairs. Great, I've got the 10 chairs I'm going to sit the students in. Now what do I have to decide? In those 10 chairs, I have to arrange my kids, right? Are you with me? Now that sounds like a what? A permutation, because I'm actually, the order in which I sit them down would have an effect on the outcome. So how would I do that then? If the order does affect the outcome. I've already chosen 10 chairs. So in those 10 chairs, I'm going to place my 10 students. 10 factorial or 10 P10. So I could say times 10 P10, but we know 10 P10 is 10 factorial over 0 factorial. Now, here's the curveball. What does this leave me with? So that is this, but this is 12 factorial over 2 factorial, which is really what? 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. Doesn't that look like the first 10 numbers in 12 factorial? What's another way of saying the first 10 numbers in 12 factorial? 12p10. 12p10 is another way of doing this. But you could think about it this way. Or you could basically say, wait, there's 12 chairs. I need to pick 10 of those 12, but the order in which I pick them and count does affect the outcome because I'm placing 10 of those kids in those 12 chairs in certain orders. But you could also break it up into two parts and think of it this way. Both of them end up making the same. So if you said that initially, awesome. If you're thinking this way, wait, first I got to decide which chairs I'm going to use. And then that's what I did when I actually arranged this class. I decided which were the best seats. I literally went around and sat in back seats. That back one over there just seemed kind of lonely. Actually, a couple of those seemed kind of lonely, but everybody's all spread out. But I don't know why. That one just had a little bit better view than this one, a little fewer heads to look through. Like, you got a pretty great shot right through here. But from there, I'm like right in the back of his head. And anyway, whatever. I had to decide which chairs, and then I decided how to put people. I really didn't decide. I just put alphabetical order. Are y'all with me on this? I'm just throwing random stuff out there. Oh, and by the way, on number 30, as it says, is it clear whether this is a permutation or a combination? Yeah, definitely a permutation element both, right? But technically, there's kind of a combination element in there as well, even though you really didn't see it if you did it this way. Ooh, I love this problem. This is a hugely common, although they make it a little bit trickier now. I'll show you both eventually. There are 8 points on a circle. So visualize that. You got this circle, and there are 8 points on it. All right, I'm going to ask you to start drawing triangles. Well, not really, but if I were to ask you to start drawing triangles using those points, how many different triangles could you draw? And if you're actually starting to think, okay, well, I can draw those. I'm just going to take the time to draw them all, and then I'm going to count them up. I guess you could. You can be here a while. But what am I really doing when I count the number of different ways I can do that? Am I not changing the order, or am I changing the order? Like, for instance, to draw a triangle, you're going to have to first do what? Find the 3 dots you want to draw the triangle with. So let's just say I pick this dot, and that dot. First of all, does it matter which one I start with? So does the order in which I choose those 3 have an effect on the outcome? Okay, that sounds like a combination. So when I'm picking them, those 3, if I'm using a combination, how many am I picking from? I'm picking from the 8, and I'm choosing 3, and the order does not have an effect on the outcome, right? Are y'all seeing that? That's an 8C3, and I'm done. And if you had to figure that out, man, isn't it going to be a lot easier saying 876 over 32 and getting the 56 triangles you need without actually having to go through and get lucky and actually count all 56 of those, which is going to be a while. But we're going to stop right here. Now I'm going to throw something a little dirty at you. See if you can hang with me. All right. I don't know that this is on here, but it's somewhere in this book. But it's come to mind, so I'm just going to mention it. No. Okay, so I'm just going to go out to the side and talk about this one. Okay, what if I had a semicircle? Got a semicircle or whatever, and you've got 6 points here, and how about 7 points there, 4 points there? All right. how many ways can I draw triangles? Now, here's the mistake people make, the rookie mistake. Oh, well, we just did this with circles. How much different can the figure make? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11C3. Now, why would this be wrong?
Because you can't choose the 3 dots.
That's right. As I'm choosing these, eventually I'm getting to 3 dots on the bottom, right? And 3 dots on the bottom don't make a triangle. So clearly, picking any 3 from here out of the 11 is not going to work for me. So what really do I need to be doing to make triangles? Just talk to me. What are my options? You said what?
I like going from the bottom.
Okay, I can definitely use the points on the bottom, but I just can't use all 3 of them. So what are my options? So I could choose one of them and then pick 2 of these. Would those make triangles no matter what? Okay. I could pick 2 of these and 1 of these. Would that still work? Is there any other option other than 1 of these with 2 or 2 of these and 1? Any 3 of these would make a triangle, right? Now, think about the wording in what you're saying and tell me if I'm correct. Am I saying, okay, here are your situations. You can have 3 of these and 2 of these in 1 and 1 of these in 2. Or is it better to say I could have any 3 of these or any 2 of these and 1 of these or any 1 of these and 2 of these? What sounds better? I like the or, because the or is showing there are different ways for it to occur. Now, whenever your brain, whether the word is there or not, but whenever your brain is thinking and, that's the fundamental counting principle we talked about earlier. And if you remember the fundamental counting principle, it says whenever you're doing this thing and this thing, what do? The numbers, you take the numbers and you multiply. That's the fundamental counting principle. It's like there's 2 ways to flip a coin, 6 ways to roll a die, 2 times 6, there's 12 total ways to get those combinations. But that's a situation if you're doing this and this. But if you're doing or, then you add. So what am I saying here? This is what I'd be saying if I said triangle. You could pick 3 from the 7 or plus. You could pick 2 from the 7 and 1 from the 4. See where the word and comes in? Or you could pick 1 from the 7 and 2 from the 4. Are y'all seeing this? And that is a math team question all day long. Now, if you're also thinking this, could I just count all of them up and then subtract what doesn't work? Could I say 11C3, which is way too much, right? And then what doesn't work? Picking 3 from those 4, subtract off picking 3 from those 4. That actually gives you the same thing. Did anybody think that? Hey guys, see if you can fill in the blanks. We're getting close to finishing this up.
That question's on the next page.
Is it? Okay.
It's on the same. It says a quadrilateral.
No, it says, it's on the last page.
But it
The
says
rest-
quadrilateral. It's not a triangle.
Did you do it, Ro? Yeah.